All right. So last time you remember we finished with discussing fundamental subspaces, but we went very, very quickly over the last one, a left null space. And I think it will be beneficial for us to go over it quickly again, because we just ran through it. Also, just for information, I updated the slides since last lecture for this lecture and for the previous one. So when you self-study, you'll notice improvements. All right. So let's talk about left null space. So the left null space is, as we said last time, the orthogonal complement of the column space. And we actually will define it as the space of all vectors y orthogonal to the columns of A. That is what we will define as left null space. So here's the definition. You can think of left null space as a space of vectors that not only cannot be produced by operator A, but the closest vector to them that can be produced by A, the zero vector. Okay. All right. We'll later prove that A is left null space A is equivalent to the null space of A transpose. Let me take get a drawing pad. I'll try to illustrate my point using the drawing. Right, well, I'll be setting it up. From the last lecture, did the ideas of the column space made sense? Like, was there anything particular about the last lecture that that was a little bit difficult? Well, we are on the same slides.
Sorry for interrupt, sir.
Yes.
But sometimes you talk about partial solution. Did you mean particular solution?
Yeah, particular solution. Yeah, I mean particular solution.
Okay, thank you.
Sorry about that. Yeah, if it's a particular solution, of course. All right. Repeat. So just as an example of what is meant here, what do you mean by the space of vectors that not only cannot be produced by A, but the closest to them is the closest vector that can be produced is a zero vector. Well, let's say A can only produce vectors in this direction. Well, let's say A is equal to 2 and 2. Well, then vectors in those directions on the plane, vectors in those directions cannot be produced by A. Moreover, the closest to them that A can produce is a zero vector, right? Like this, for example, is even further apart from what A can produce. Okay, so that would be left null space of A in this case. Left null space of A, in this case, like as a basis in the left null space of A, would be, I believe, something like minus square root of 2, square root of 2. Something like that. Let me manage the chat. All right. Good. Now notice this promise. We'll later prove that the left null space of A is equivalent to the null space of A transpose. So we'll do that today, just a little bit later. Same as I promise you will prove that row space of A is the same as column space of A transpose. Okay. Now we can project vector y onto the left null space of A. How we do it? Well, we know how to project y onto the column space of A. That would be a pseudo inverse y. That will be the projection onto the column space. The projection onto the left null space, what is it? Well, it is y minus the projection onto the column space, right? So this is how we get this formula. How did we get this formula? Well, y is equal to its two orthogonal components. By the way, if some of you in the chat want to talk, feel free to unmute and talk. But after that, please mute yourself because we have this constant feedback, which will be on the recording. Is it good? Okay. Just to make sure that you know, while you are not talking, you're muted. Okay, good. Now, if we have orthonormal basis in the null space, in the column space, sorry, of A, then the projection can be written as such. Why? Well, because for the same exact reason as before. Like the projection is actually like the more general formula would be projection to the left null space would be identity minus projection into the column space, projector into the column space times y. And how this projector is formulated doesn't matter. It can be formulated this way, can be formulated this way. Both are projectors onto the column space. And today we will also prove that this is equivalent to this. We'll actually prove that those two projectors are exactly equivalent. So both ways are just a project.
I'm sorry, is YC is a projection of A to the column space, right?
Yeah, C is projection to the column space, the one I draw here.
Because left null space is orthogonal to column space.
Yes. Not just orthogonal, it's orthogonal complement to the left null space. The difference between orthogonal and orthogonal complement is, let me show you. Let's say two vectors. This vector and this vector are orthogonal, but they are not bases in orthogonal like the spaces that they span are not orthogonal complements of each other. Why? Well, orthogonal complement for, let's say it's A and this is B. Orthogonal complement of A, let's say span of A, its orthogonal complement is actually the basis in the orthogonal complement. Is this thing. So if two subspaces are orthogonal complements of each other, it means that the direct sum is going to be the whole space. So it means that any vector can be represented as a sum of two components, one line in one space, another line in another space. So that's why complement matters. But yeah, orthogonality also, of course, extremely important. Okay, moving on. Now, I will give you a few interesting examples how to use this knowledge. And then I will move to SVD. And then I will prove what I promised to prove today. I will try to go quickly because there is a lot of material, and but stop me as soon as you have questions, okay? All right. So given this system, x dot equals to ax plus bu, find if there are states that can be made into fixed points. Fixed point, remember, is when x dot equals to 0. It's what it means to be a fixed point.
Equilibrium?
Come again?
Is it equilibrium or stable point?
It's called fixed point. You can say it is equilibrium, but the terminology is fixed point.
Oh, okay.
So ax plus bu is a fixed point equal to 0. Okay, so find if there are states that can be made into fixed points. And states, by the way, notice state is x, right? All right. So if and whether or not, like, what do I mean made into fixed point? Well, ax might be equal to 0, right? But that doesn't make it a fixed point of this system. Like, it would be a fixed point of this system. But for this system, what we want is that ax plus bu equal to 0. So to make it a fixed point, we need to have such u that column x is a fixed point. Okay. Now, and to find all states that can be made into fixed points with a constant control law. What do you mean constant control law? It means that u is equal to some u star and nothing else. So it's just a constant in time control input. By the way, fixed point does not imply stability. It just implies that if system is exactly at the fixed point, it is going to stay at the fixed point, but it has nothing to do with stability. It can be unstable, of course. Like with the constant control law, it will be unstable most. Okay. So first question. If there are states that can be made to fixed points, oh yes. This guy, x equal to 0, becomes a fixed point under this control law, which is a constant control law, or with this control law, which is a typical linear feedback. This is not a constant control law, notice it is a linear feedback. But both make this a fixed point. How? Why? Well, let's check. X dot equals to a times 0 plus b times 0 is 0. So check. X dot, we'll check now this one, equals to a times 0 plus b times minus k times x. X is 0 times 0. This is 0. This is 0 equal to 0. Check. So indeed, trivial fixed point exists. Trivial because x, that's what we call is 0, trivial. All right, so indeed, at least one exists. Now let's find all of them, all of the states that can be made into fixed points.
Sorry, sir.
Yes.
If you are multiplying k by x and x is all is 0, so why this minus? Just because it's a typical feedback, or
I mean,
because of,
no, I mean minus 0 is equal to 0, right? So yeah.
Yes, sir, but why it's not plus kx? Or plus minus kx.
I don't understand the question.
You are typing u is equal to minus k multiplied by x.
Yes.
Yes. Is it for because of differential equation to be from x dot?
No,
equal to
I just define. I just say that those two examples of control law makes this into a fixed point.
Okay, sir. So why don't you just write minus plus?
You mean why not this control law?
Plus, yeah. So that's right.
I mean, yeah, this control law would also make it into a fixed point. That's true.
Okay, so thank you.
No, but the reason I didn't include it in the examples is because it is not what we usually see in the classes, in the control class. But you know, what is interesting, so those two control laws, let's just consider them. If you, this is a 1, this is a 2. So 1 would give us closed loop system of this form. And I think that is very familiar to those of us who studied more, you know, classical control theory in the technical oriented class. I think probably most of you saw it this way, right? This second control law would give us closed loop system of this form. On the first glance, it would look like this is correct because it is negative feedback. This is incorrect because this is positive feedback, right? And indeed, it kind of looks like it might be incorrect, but actually, they're exactly the same. The reason is because you didn't specify how you choose k, right? K would be different between those two. If you choose this form, k would be one thing. If you choose this form, k will be another thing. The difference would be that k will absorb the minus sign. That's all. So when you define this control law, your k will absorb the minus sign. And usually this way control law is defined in optimal control, at least if I remember correctly. When we do optimal control, we often define k this way. Whereas this way, it is defined in classical control, in LQR, PID, etc., etc., etc. So they are just, those are the same thing. All right. Now let's find all states that can be made into fixed points with constant control. Well, what I'm asking is actually this, right? We have this equation. This is a constant control law. This is the states that we are looking for. And all of this should be equal to 0. Well, what is the space of solutions of this equation? Well, we know that what's the space of solutions of this equation, right? First of all, it's not going to have a particular solution. Why? Well, because you know, can someone answer for me why it's not going to have a particular solution?
Because like particular solution related with the space. When are we searching for a value, a non-zero solution? When the output is non-zero.
When this guy is non-zero?
Non-zero, we have a particular solution.
Yeah, but why is this not going to have a particular solution?
Because all the null space will satisfy this equation.
That is actually correct, but okay, you know, is a good answer, right? But let me just put it this way. Particular solution is when we have non-homogeneous equation, right? When we have equations of this form, homogeneous equations, solutions to those equations are given as a null space, and you don't have particular solution. When you have not homogeneous equations of this form, you have a particular solution plus null space solution. Like the difference is that here particular solution would be given as x equal to a pseudo inverse 0, which is 0. Any matrix times 0 is 0. So this makes sense to talk about particular solution because of this, right? While here you can have a particular solution. So just to remind you, so it's has to particular solution, whether or not it needed, depends on what you have after the equality sign. Like this is 0, so like, no particular solutions here.
Извините, слышно меня?
Да.
Извините, particular solution на русском это, ну, в смысле, типа, ну,
Частное решение.
Частное решение, то есть когда одному b только одно решение x соответствует.
Нет. All right, we'll go back to English because I don't want to have long discussions in Russian.
What is the difference between like unique and particular solutions?
Oops, sorry about that. All right, we'll discuss one more time. Remember, but I want to draw your attention that we discussed it last time. So just just to make sure that we. But we also don't have recordings of the last lectures. It's not easy. All right, let's try to give an example of what is the meaning of particular solution versus unique solution. Okay. Let's consider this equation. X1 plus x2 equal to 5. Apologize for horrible handwriting. For some reason, maybe my drawing pad is worse, but for some reason, last few lectures I wasn't able to use it cleanly. X1 plus x2 equal to 5. So, does it have a unique solution? Please answer with me. It's it's a very simple question. So let's just
No.
No, of course not. It has multiple solutions, right? Like for example, as long as x1 is equal to 5 minus x2, that is the solution.
Infinitely many.
Yep. Let's just provide at least one solution. One solution is this. Another solution is this. Another solution is this. Okay. Good. So the space of all solutions to this equation would actually be given as, let me just define x as x1, x2. And this space of all solutions x would be given as any one of those solutions, particular, or say particular here. Except those are not like particular solutions as in like they're not in the row space. That's what I'm saying. They're not in the row space, but they they will suffice for given all the solutions plus null space times z. What is the null space of this system by the null space spaces? I would claim it is something like this.
1, -1.
Yeah, one negative one indeed. But I would normalize it, so would do it this way. But yeah, it's a very good eye. You managed to find it. Times that. Where that is the real number. Right. So this is the answer. Like take any of those and add this guy. That's space of all solutions. If you want this guy to be in the row space, so then you would need to solve least squares for this problem, and then you would find what we prefer to have here. What we prefer to have here is a least square solution. So least norm solution. The smallest possible x by norm that would satisfy it. I sort of suspect maybe this is the answer, but we're not going to spend more time on it. Is that was that sufficient?
Yes, thanks.
But is it necessary that the particular solution is the least norm? Like, not for this example in general.
Come again?
Like the particular solution for AX equal B, is it the least norm solution?
Particular solution, least norm solution. Okay, so let me do this. So AX equal to B. You're asking whether or not some particular solution is the same as solution to least squares.
Yes.
Yes, indeed it is. What should I say? Particular solution is not like any solution to this equation is particular solution. Any solution, like you take any solution to this equation, it is a particular solution. But one of them is least squares. And we just prefer it because it is unique and has the smallest norm. But you can use any solution to this equation. What's like, just solve it any way you want, and you get a particular solution. It's just not going to be the smallest norm if it is not least squares. That is all the difference.
So can we get any solution and project it into row space to get the least norm solution?
Yes, we can do that. Okay. Or we don't have to even do this. Like in some cases, all we want is to just write out all solutions. And in this case, you don't have to find least squares one. But by the way, remember that if you have a particular solution, let's say some particular solution 0, and you want to find least squares, projecting it into the row space of A would look like this. Unless you know the row space spaces. So this would be, this is the way you would find this least square solution by projection. But notice that you could also do it this way. So same operation here. So if you're going to do this operation, you may as well do this operation. But if you know the basis in the row space of A or in the null space of A, then maybe you could do it cheaper without pseudo universe. So anyway, that all of this is just to draw your attention how computations work. Anyway, let's go back to the slide. So let me annotate again. Given the system, so another problem. Given the system, find. No, that's next problem. Let's go to the next one. Okay. So given the system. Oh wait, did we solve the previous one? I don't remember. We were talking so much that I don't remember if we solved it. Let's quickly call. So we need to find all fixed points. How do we do it? Well, we consider again this equation: x star plus bu star equal to 0. Now, how do we find space of all solutions? We consider null space of this matrix. And we find this orthogonal basis in the null space. And that is the space of all pairs control, state control pairs. It spans space of all state control pairs that define fixed points and constant control laws that achieves them. Now we want only space of all fixed points. Well, we slice the first n rows of this null space basis. Remember, null space of this matrix is going to be n plus m rows high, because the rows of the null space is columns of the original matrix. You slice the first m rows like this, and you get new matrix n, which would give you space of all fixed points like this. That's it. That's how you find all of it. Like, it sounds complicated, but what you do is just look at this equation, write it as I wrote here just a minute ago. Then get this null space of this matrix. And in MATLAB, you just call, in Python, it will be the same, but just familiar MATLAB thing. And I don't, I'm starting to forget syntax. I think you would call it like this, right? Let's say 1 n. That would be the first n columns. I'm unsure if the square brackets or normal ones. Anyway, that's how you find it. Let's move to the next one. Before I lose you to boredom, I think with those examples, that is the risk equivalent to losing you to difficulty. Okay, same system, but now I want to check if a particular x star can be made into a fixed point, and I want to find u star that makes x star a fixed point, given that control law looks like this. That is actually very typical. That's called feed-forward control. Like, someone designed feedback. They used LQR to find k. But now you need to find this component of the control law, because you want the robot to stay at this state. You could avoid this completely by transferring the whole thing into error dynamics. But, let's just say you look at it this way. Okay, what is the solution? Well, first you substitute this control law into the system. And what you get is x dot equals to ax minus bkx plus bu star. And this is star, this is star. All right, so this equation. We check that it has a solution. What does it mean for it to have a solution? Well, if we rewrite this thing as bu star equals to minus a minus bk x star, what we care about is whether or not this guy lies in the column space of this matrix. If this guy does not lie in the column space of this matrix, B, then there is no such U that can produce this guy. And conversely, if this guy lies in the column space of this matrix, then there is such U that can produce it. Then that means that there is a zero residual solution. Okay. So all we need to check is whether or not this guy lies in the column space of B. How do we check if something lies in the column space, in the subspace? We check whether or not it doesn't lie in the orthogonal complement. So the condition is done by projecting it into the left null space of B. This has to be 0. So this is a condition whether or not it has a solution. Notice it depends on x star, but also on this and on this. So this is how we check whether or not X can be made into a fixed point. I'm sorry. Now, second point. We have U star. And we want to find, well, sorry, we have X star. We want to find U star. How do we do it? Well, remember this equations that I wrote here a moment ago, right? BU star equals to minus A minus BK X star. We just find its least square solution. Sorry, yeah, least square solution. Since this condition proves that it has a zero residual solution, or it will prove that such U doesn't exist, like one of the two. You know, if this condition checks, then simply doing the least squares, so saying B pseudo inverse times right hand side gives us a solution, and that's exactly what is written here. Now, I want to draw your attention to one important detail that you might have missed. So this check here answered the first question, right? But it didn't do just that. If I was only asked second question, I couldn't do this and be satisfied. Why? Well, because this would provide me a solution always, unless B is 0. Even if B is 0, you can technically provide me a solution. So what is the problem with that? Well, the problem is that I would get a solution, but the solution would not actually make X into a fixed point. It would be just the U that is closest to making X into a fixed point, but doesn't do it. You know, what is the point of getting a solution that doesn't actually satisfy the premise, making X into a fixed point? There is no point.
Sorry, I had some sound problems later. Before, is fixed point is equilibrium?
Fixed point is when this guy X dot is equal to 0. You can say it is equilibrium.
Okay, thanks.
Yeah. But don't mix it with stability. Stability is like stable equilibrium, unstable equilibrium, both would be fixed points. But yeah, equilibrium. Yeah. So pseudo inverse can very easily give you solutions, but they are not always zero residual solutions. So you need this condition to make sure that the solution is actually zero residual solution. Of course, you can just solve it, substitute it, check the residual. Or you can just check the condition and then solve it. The amount of computational effort is something you should check for yourself, like for each individual problem. But I'm just drawing your attention to the fact that you cannot simply solve it and be done with it. Okay. And if you solve it and you find something is wrong, think about conditions like this. Okay. Let's move on. We'll just have a couple more examples, maybe one, I don't remember. And then we'll move to the next topic. But let's try to still pay attention to the examples. They are illustrative of what you can do now with your tool set. Notice that even here we already used left null space projections, column space. Previous example was null space, row space for the particular, row space we didn't use, but we talked about it. Okay, now. Again, same system. We have a state which cannot be made into a fixed point under constant control law. And we want to find closest to its state, xf, which can be made into a fixed point. Okay, so we know this cannot be made into a fixed point, but this should be made into a fixed point. And we want to find this, which is as close to xd as possible for this system. So you can think about it this way. Your quadrotor cannot really stay in the air tilted. So I give it state, like I will give it desired coordinates. I say, okay, angles 10, 5, 5, coordinates 2, 3, 3, velocity 0, 0, 0, angular velocity 0, 0, 0. Please stabilize. And your system will tell you, well, the angles don't make sense because pitch and roll cannot be 5 and 5 for the quadrotor to be still stable. But if they're 0 and 0, everything else can be achieved. Like yaw can be achieved, coordinates can be achieved. So this is kind of like illustration of this problem. Of course, in this quadrotor, it's quite clear how to nullify those things, but in general might not be. Okay. So we remember that the state of space of all fixed points is actually this, right? So we don't need to solve it second time. For this system, here is a space of all fixed points under constant control law. Well, how do you find xd, xf closest to xd? Well, all we need to do is to project xd onto this subspace, onto the column space of xn. Oh, sorry, nx. So this system is now you can think about it as a linear system, right? And you want to find such xf, which would be closest to xd in the column space of this system. Well, just project it there. So this is how we project onto the column space. And thus we found xf. So see, like zero pain was very simple. Just recognize that this is what we already found and remember projections. Notice here we cannot substitute nx transposed. Why? Because this is not orthonormal. N null space was orthonormal, but this is not n. This is first n rows of n. So this is not orthonormal. This is not orthonormal. This is. So, keep in mind those details. Okay. Any questions? This might be fast, but you know, you will also have time to self-study it afterwards. I just want to point out like the possibilities of using fundamental subspaces. You're not required to memorize any of this. You know, I told you how to do projections. Now I want to kind of give you an idea how they can be useful. Okay, I think maybe it is the last example for now. So given the same system again, but now with C and linear control law, affine control law actually, find all states that can be made into a fixed point by choosing appropriate U star. This is similar to the first question, except we have C now here, and we have a linear part of the control law. So we will just write this equation for the fixed point. And we define V as XU. So what does it make us? after we define v, we get this equation: a minus bk, b times v equal to minus c. That equation becomes this equation. And then you can find particular solution this way, same as before. There is absolutely nothing new here. And you can find null space solution. And that is a solution. And here is a solution to the original question. First 10 equations will be x stars, or the rest u stars. So notice that the question looked complicated, but all it took is just to rewrite it as a linear system. And after that, there was nothing new.
I'm sorry, sir.
Yes.
Why you did not check if minus c lies in the column space of
Yeah.
what?
Yes.
Before you apply
yes,
the second one?
Yes. Yeah, that's great. We indeed, if we want to check that at least one solution exists, we needed to check if C lies in the column space of this matrix. How do we check it? How do we check that?
If we can see if its projection on the left null space equals 0, then
Exactly. That's great. Okay, that is very, very good. I can write it out. It will take a little bit of space, so let me just see if I can write it. I think it will be something like I minus a minus bk b a minus bk. Sorry for the horrible drawings. B Pseudo Universe, and then here we'll have C, and this whole thing should be equal to 0. We can add the minus sign, but it doesn't matter. I think, yeah, so this will be the condition. Good eye, and good job, you got the idea. I'm very, very happy. The idea that you need to check, because indeed this solution may fall flat if this guy has a residual. Right. You notice by the slides that there is one more example, but I'm skipping it for now because it is a much more difficult example than all the previous ones. Previous examples were solved in one slide. This example requires 1, 2, 3, 4 slides. So we're skipping for now. If we have time at the end of the lecture, I will show you. If not, do it as a self-study, or I will show you some other time. I will see. But it is extremely interesting, but very difficult. All right, now we'll have a 5-minute break. And give me a second. We'll have a 5-minute break. And then we'll have a singular value decomposition as our next topic. So we'll start in the, it is 11:30 by my clock, 11:35 we'll start. All right. Now, let us move on to our next topic for today. It's not going to be very difficult, so don't worry. It looks,
also,
you know.
By the way, Professor, you didn't refresh the slides in the Git. Like there's no such slide.
For single value decomposition. They're probably they are on Git. They're just somewhere in a folder. Like if you look through the content, like folder slides, scroll down, you will see SVD folders there. I just didn't update the README. That's all. There's
maybe the fact that confused me that the lecture flow is different. But okay, we will look for it. But
yeah,
okay, let's continue.
Right. So single value decomposition sounds scary, but we're not going to discuss anything difficult today, actually. Like singular value decomposition is one of those things where you can easily spend hours discussing two different lectures on singular decomposition, and they won't even have anything in common. Like I recently read a chapter on this topic in a classical textbook on math published in Bauman State University, and there was a very interesting information there, but it's not going to have any intersection with what I'm going to give in this lecture. And so, you know, is how should I put it? Like you probably in your life already experienced SVD, and you probably already form an opinion. Just make sure you don't allow this opinion, if it is negative, to guide you, because SVD can be discussed in difficult terms, in simple terms, and can be discussed in terms that are friendly to modern computations and unfriendly. You can start to discuss it in relation to what do you call it, this Gram-Schmidt orthogonalization process or some other related technique. There are many ways, but just make sure you don't judge the thing itself by how it's taught. Like what I'm going to talk right now about is not all there is to SVD. SVD is a rich topic. So, all right, let's just jump into it. So normally SVD is written, I think, as something like this. You have matrix M. You say that is equal to U big sigma V transposed. I think that's how you usually write it in like Wikipedia, in many of the standard textbooks, etc. Is nice, but I'm going to write it this way I wrote it here. I think that is actually more easy for us in this class. And this is the same thing, right? I just wrote, this is U, this is V transposed, this is sigma. Notice I explicitly wrote the structure of sigma. Sigma is a diagonal matrix, sorted, meaning that the first element of sigma is the biggest, sorted by decreasing order. So the first element would be biggest. This is the first element of a diagonal matrix. You understand what I mean, right? Like this is the biggest element, this is smaller, etc. The rest is zeros. I probably shouldn't write it as I shouldn't write it as what they call it, as circles, because like this element is biggest, this is smaller, etc. Okay. And notice that it has blocks. So this block is completely made of zeros. This of course, right, because it is diagonal matrix. But this is also a block of zeros. Okay. Now, let's try to make sense of what we see here. Let's try to make sense of it. So first of all, let me point out that what those things are. Oh, this is our original matrix. This is the same exact matrix. So the equality sign here means what equality always means. It is the same matrix. It's just written in this form. Okay. So if original matrix could be put into this equation, this matrix can be put into this equation as well. Okay, that is first important thing to note. This is not a change. This decomposition does not change the original matrix. Second, this is row space basis. This is null space basis. This is column space basis. This is left null space basis. So somehow SVD decomposition gives us all those things. That is surprising. That's probably not something you saw before, but that's indeed the case. I'm not going to prove it. I'm just claiming that this is how SVD decomposition works. But in a sense, I think it will be easy to prove. If you know, by definition, those matrices are supposed to be unitary. If you read this in Wikipedia, where they like abstraction levels, or orthonormal in our layman terms. And so, you know, they're supposed to be orthonormal. And if this matrix is orthonormal, then this automatically implies that two components of this matrix would be orthogonal complements of each other. Same as this guy. But it's okay. We will skip the proof. But I'm just giving you like an idea of how you can try to prove something here. Okay. Now, what is sigma? Sigma is a matrix of singular values. So sigma, I will draw it once again, is like, we have sigma 1, sigma 2, etc. They're related to eigenvalues and to other things. We're not going to discuss what exactly they mean, but you can think about them as weight coefficients. There is another way to talk about SVD, which is famous. You say SVD is rotation, scaling, and rotation. Why do we talk about it this way? Well, as I said, those two matrices are orthonormal. And orthonormal matrices represent rotations. So what this says is you can rotate something. And by the way, since this matrix is full rank, both of them are full rank. Transpose is also a rotation matrix. So you rotate something, scale it, because diagonal matrices are scaling, and then you rotate it again. So that is how people often talk about SVD: rotate, scale, rotate. And you get any matrix this way. But by the way, that should also tell you that simply scaling and rotating once is not enough. Okay, good. Now, this you can think about it as scaling coefficients, or stretching coefficients. But don't worry about it. Like sigma, we're not going to use it a lot. So if you have questions about it, just keep them. You can ask them to Wikipedia and so on. For this class, we won't need to dwell deep into sigma. But of course, there are hundreds of applications where sigma is exactly where you need to dwell on. So, don't dismiss it, of course. All right. So this is SVD decomposition. It has just this structure. Now notice that because of those zeros, we can actually, when we multiply this guy by this guy, this thing goes away. It doesn't actually, it multiplies zeros. It goes away. So you just have R transpose, like Xi, big Xi times R transpose, and 0, right? Big sigma is, sorry, not Xi. You have this situation here when you multiply this together. And when you multiply this by this goes away because it's multiplied by 0, right? And you end up with this expression. So you can think about SVD decomposition in these terms. That would be entirely correct. SVD decomposition would actually give you something like this. And programmatically, when we talk about SVD, let me get rid of this. When we talk about SVD, we often talk about two types of SVD. Full SVD, this thing, where it will give you all of this information. And economical SVD, this type. All right, so what is this block of zeros? Where does it come from? Well, it has to do with rank. What is the rank of a matrix? Well, we can give definitions of what a rank of a matrix is, a number of linearly dependent columns, for example. But the way, if you ask MATLAB what rank of a matrix is, you would ask MATLAB like this. What it will do is it will call SVD. It will get some diagonal matrix here. It has cut-off ratio. And I'm trying to remember how MATLAB defines it. Toll. It's called toll. You can provide it, or MATLAB will compute it by itself, based on the size of the matrix, I think. And then this tolerance, it will apply to all elements of the diagonal of this matrix. And it will find how many elements are bigger than tolerance. So basically, yeah. So, and then it would just find the sum of those elements. So, sorry, number of those elements. And that's the rank. Second. I'm sorry. So this is a rank. Rank is a number of elements on the diagonal here, which are bigger than 0. So
if,
yes,
if the matrix, if the original matrix is invertible, so sigma will be identity matrix, or does it will it have also
no, that would be diagonal matrix.
Yeah, okay.
Not identity, but just some diagonal.
Yeah, I mean diagonal. Okay.
So if it is invertible, if A is invertible, it means it is full rank, right? If it is full rank, it means, let me just get a white screen for a second and we'll discuss full rank. So let's say A is full rank, M is full rank, sorry. Well, first of all, it means that here we would have just some, let me just even write like this. We would have some sigma here, which has all, like it's again full rank matrix, sigma itself. It doesn't have a block of zeros. Like normally we see this situation, right? With normal matrices, but full rank matrix is not going to have this situation. So this is going to be the diagonal matrix with all of its element, like without a block of zeros here. Normally, what we see here is this situation, right? But since we don't have this block of zeros, we don't have this whole row, so we don't have any null space. So here is just R transposed, because N just doesn't exist. for null space doesn't exist for a full rank matrix, of course, right? By definition, null space is a space of all vectors that matrix maps to 0. But if it is full rank, the only vector it maps to 0 is 0, right? I don't know if you studied linear algebra in this way, but full rank means that the linear transformation that the matrix represents is, how do they call it? Invertible, meaning that for any element in one subspace, this matrix gives an element in a different subspace. But this element can be, original element can always be obtained by inverse of the transformation. It is one-to-one relations. And that means that if there was a null space, then multiple elements of the original space would be mapped to a single element of the new space. And you wouldn't be able to find inverse. So it wouldn't be full rank. So full rank implies trivial null space. But also trivial null space, it also implies, notice, so this, the lack of this column implied lack of this guy. Lack of this row implies lack of this guy. You cannot have a left null space because you don't have this, right? So we just have C here. And again, in terms of linear transformations, what you can say is, if there was a left null space, it means part of this space where the matrix points would not be reached by the linear transformation. So, you know, that means that some of the elements here won't be mapped back. And that, you know, it will be a little bit more difficult to prove that this is incompatible with the original definition, but you can do it. I think we're arguing about dimensionality of the spaces. They're the same dimensionality because there's a square operator, and you cannot have this situation with a space of same dimensions. And yeah, so that would be impossible. But anyway, at the very least, it is impossible because of this lack of this row. This row doesn't exist for full rank matrix, so nothing to multiply L with. Okay, so for full rank matrices, SVD already looks like this. Like not economical SVD, any SVD looks like this for full rank matrix. Okay. Good. So I hope now this is a little bit more familiar when we look at it. Doesn't look as scary. Number of diagonal elements here is a rank. This is column space, left null space, row space, null space. That's it. Okay, let's move on and see how we can use it. Well, first of all, rank is the size of this matrix, right? As I said. Now, what is a pseudo universe? Pseudo universe is defined as such. You simply transpose the whole thing and replace this with the inverse. So you see where before we had R and N, we have C and L. There was C and L, now it's R and N. Here's the inverse. And for full rank matrices or any other matrices, we can always simplify it to this form. Notice that in both cases, this simplified form does not involve L or N. It only involves R and C. So null space and left null space never play any role in actual SVD representation of a matrix. They only play a role in other computations, but not in SVD itself, in the decomposition itself. Like we don't need them to recover A or A inverse. And by the way, this is how a pseudo inverse is actually computed. Like you would think that what I'm showing you here is just some, like smart formula. No, it's not. That is how MATLAB computes it. This actually is like this is how MATLAB computes SVD. Python probably does the same thing. You can open the code, by the way. You can type open pinf, pseudo inverse, sorry, not SVD. Open pinf, and MATLAB will show you the code how pinf is computed, and you will see it does it this way. Just check it after the class. It is very, very instructive. Okay. So now we know what a pseudo inverse is in terms of SVD. And remember, there was a formula for pseudo inverse. It was, I'm risking making a mistake again. But I really, really don't want to make a mistake, but let me try it. I know for sure that it has to be something like this, right? And I think, sorry, I think it would be like this. Huh? Right? I think so. Whatever. So anyway, this is the formula that exists for pseudo universe. No one uses this formula because it includes this term, which how you're going to compute it. What is the way to compute inverse? There are no stable algorithms to do it, to compute exact inverse. If you're going to compute pseudo inverse with this guy, then it is a circular definition. So instead, we use this. And by the way, it looks like a circular definition here, but it is not. Why? Who can tell me? Someone answer me. Why this is not? This is easy to compute.
Can you repeat the question, please?
Why this term, while it contains inverse, is easy to compute? I just claimed that this is impossible, like impractical to compute. But why is this not impractical? Why is this easy?
Maybe because it has small numbers.
No, no.
Because it's diagonal, so all
Yes.
the columns are independent.
No, not even close. It is diagonal, and inverse of a diagonal matrix is
The transpose.
No. Let me just write it even like this. Inverse of a diagonal matrix is just 1 over its elements. Right? You're familiar with this fact, right? Let me, I mean, just in case you need a reminder. Let's say you have this linear system. 3x1 equals to 5. 2x2 equals to 2. x3 equals to 2. How do we solve this problem? Well, we need to represent it as a linear system, obviously, right? We cannot just solve it. We need to represent it as this, this, and this. Times x1, x2, x3 equals to this guy. we can see that this is full rank matrix, so it would have trivial null space, so it would have only a single solution, right? And the solution can be obtained by inverse. We don't need to discuss a particular solution or anything else like least square solution, because it has only a single solution because it's full rank matrix. Well, how do you find the solution? We need to invert this matrix. Okay, but before we invert this matrix, let's just solve it how normal people would solve it. Normal people would just say 5 over 3, 2 over 2, 1 over, 2 over 1. And indeed, that's exactly how those matrices are inverted. Right? It's just 1 over 3, 0, 0, 1 over 2, 0, 0, 0, 1. You get the idea, right? Sorry for making such an obvious example, but the fact that the inverse of the diagonal matrix is inverse of its elements is extremely important. So I wanted to make sure that we all understand it. Okay. So this is why this is okay, while doing something like this is not okay. Like this can be any matrix. And how do you find the inverse of any matrix is a good question. This is a diagonal matrix, you just divide. Like in MATLAB, I think this is written as something like diag of 1 point divide sigma, something like this, where this is element-wise operation, this is diagonalization of a resulting vector, and this is a vector. So you can see it is very simple. Okay, so this is how we compute pseudo inverse, and this is how we compute rank. No questions? Can we move on? Okay, I'll move on. Now, let's find SVD decomposition of A transposed. Well, it has the same form, right? To be CL, RN, C. I'll just denote it with the subscript T for transposition. Okay. Now, we transpose it, transpose this thing, transpose this whole thing. Because remember, they're the same, right? Keep it in mind, they're the same matrix. And we remember the diagonal matrices transposed as the same as, no, not transposed. Transposition doesn't change anything for a diagonal matrix. So we transposed both parts, and what we got is this whole thing went here. This whole thing went here, and you see the result. Okay. And you can see that for this original matrix, not transposed, its column space is supposed to be here. But now we have here a row space of the transposed matrix. Its left null space was supposed to be here. But we have here null space of the transposed matrix. And same here. So what we find is that row space of the original matrix is a column space of the transpose. And that is, yeah, row space of the original matrix is a column space of the transpose. And that is how we compute a row space of the matrices often in practice. When we, in MATLAB, we only have this orth, and we are too lazy to use SVD, we can just use this to compute a row space basis. Null space, left null space of the original matrix. Left null space of the original matrix here is the null space of the transposed. So if you want to compute left null space, we can just call this. This will give us left null. This is lazy. Like a smarter way would be to compute all four for the matrix using a single SVD and avoid calling them twice. Sometimes this is irrelevant. Like if you're only going to call them once, go ahead. But if you're going to call them twice, you're doing two SVDs, and that is irresponsible. You should only do one SVD. Otherwise, you're wasting computations. All right. So I promised you we proved it. Any questions regarding this? Right. Move on. You'll be able to go over it on your own time. Just think about it. But you can see the argument laid out here. Now, let's just prove a few interesting facts. First of all, let's prove that this is the same as this. How do we do it? Well, we remember what A is, right? A is C sigma R transposed. And A pseudo inverse is equal to R sigma minus 1 C transposed. We just had it on the previous slides. So we multiply them together as here. And then we notice that this is just identity. R transpose R is identity because it is inner product of a orthonormal matrix. So it's nothing, like it goes away. This is by definition identity because matrix times its own inverse is identity. And here we have it. What we wanted to prove, we just proved it. See, it is painless and extremely simple. And that is, this result is not profound by any means, but I would want to draw your attention to the fact that what we obtained here is 3 lines that proved something that looks quite bizarre on the first glance. And you already knew that it's true because, you know, I told you so, etc. But sometimes in your life, if you do a lot of algebra, what you'll find is you would want to prove something or check if something is true of this ilk. You would want to see if maybe 2 expressions are equivalent or whatever. Just use it as one of the instruments in your tool belt, the SVD decomposition. Because in SVD decomposition, there are a lot of, like, matrices are either diagonal or orthonormal. And that creates a lot of properties which you can use, like those type of properties. So just treat it as yet another way to prove stuff. You can see it's very simple. Let me just show how you can use it to prove more interesting things. Let's prove that this is the same as this. Oh, again, just write what inverse is, write the original matrix. Notice that this is indeed identity. This is identity, and here is the proof. Okay. Any questions about this one? So you see, it took like a second. Okay. Next, what we can prove. 1 second. Sorry. My apologies. So next, let us prove something quite interesting. This is a projector, right? We can prove that a projector times a projector is a projector, right? That this is the same thing. How can we prove it? Well, let's just rewrite it this way. And what we have is this ridiculous expression. This, and this. Notice that indeed this is identity, this is identity, this is identity. Right? So what we have here is, again, two identities. And thus what we have here is this guy. But this guy we just proved before is equal to this guy. So we just proved that P times P is equal to P. And that is true for all projectors. This is just a fact about projectors. Okay. That is quite interesting. I would recommend you try to think if you can prove anything about those types of things or about those types of things. This doesn't exist, by the way, but this does. So, by the way, just for yourself, prove why projector cannot be full rank, why this should not exist. It's that doesn't even require SVD, but you can use SVD, of course. But projector shouldn't be full rank. All right, so that is what I wanted to show you regarding SVD. Do we have any questions? Because I think that's the last slide for this lecture. Yep. Do you have any questions? If we don't, depending on time, I don't know how much time we have still. We can go through examples, but how much time do we have, guys? Do we have any time?
No, sir.
We are out of time, right?
Yes.
Okay, sorry about that. All right, then we like this difficult example that I told you about. You're free to explore it. Is 4 pages of slides, and last year I struggled giving it, but now I think it is modified, and you can go through it by yourselves. I don't think we will have any more lectures on algebra, so this is the last one, and starting from tomorrow, next week, it will very quickly go into convex optimization. But this information here not only is a prerequisite, but also in its own right, I think one of the extremely useful tool sets. So, when you prepare, I would recommend you to just invest a little bit more time and try to understand details of what is done here. Because pretty much every operation that I showed you is something that I used in my research. Like, I don't think I included a single operation here which wasn't personally useful to me. out of, all the algebra. Of course I could have put here like a lot more, right? But there you go. Everything that we have here is something that I found useful. So you would likely find it useful too as soon as you start using SVD and the linear algebra in your practice. All right. If we don't have any questions, then I will stop at that. Feel free to write in the chat if you have, like in the Telegram chat, if you have questions when you self-study. Since again we finished linear algebra with that, I expect we can still discuss it during the lectures, during questions. But also, since you are going to now go through it independently, maybe consider posting your questions in the chat, so that during lectures we spend more time on convex optimization, while questions regarding linear algebra I can try to answer as they come via text. But of course, as soon as you have any question, during lecture, whatever it is, just ask. I just want us to, how should I put it? I want to motivate you to self-study it now and ask your questions during the week instead of waiting until the next lecture, is I guess where I'm going to. Yes.
I have a question, but I don't want everyone to wait. Like I tried to do the last example,
okay.
4-slide example, but I have questions. Should I ask it now or send it in the chat?
We are out of time, so people would want to have a break. No, wait. I'll end the lecture here, and after the, but I will keep the call, and whoever wants to listen to our discussion will listen. But I will stop the recording. All right, for everyone who is going to go, see you later.